The world is full of complex signals, from a musical note to an electrical vibration. These signals often look messy and complicated. This video explains the mathematical tool that allows us to see the simple components hidden within this complexity. The Fourier Transform acts like a mathematical prism, separating a complex signal into its basic frequency components. It moves us from the time domain, where we see how a signal changes over time, to the frequency domain, where we see which frequencies make up that signal. To understand the transform, we first expand our view of numbers beyond the familiar one-dimensional number line of real numbers. To describe rotation and waves in a new way, we need another dimension. Imaginary numbers create a second, perpendicular dimension. Since no real number's square can be negative, these numbers cannot be placed on the real number line. This requires us to extend our idea of numbers into two dimensions, creating the complex plane. The complex plane gives every number a unique geometric position. A complex number is written as a plus I multiplied by b, where a is the real component and b is the imaginary component. This allows every complex number to have a natural position on a 2D plane. Euler's formula provides a powerful way to describe points on a circle. Euler discovered an extraordinary connection. Any point on this circle can be described compactly as r times e to the power of I times theta. Adding time puts this point into constant rotation. If we rotate this point with a constant angular speed omega, the angle theta becomes omega t. This simple expression now describes a vector of length r, continuously spinning at a rate of omega. The shadows of this rotation are pure sine and cosine waves. When we plot the vertical and horizontal positions of the rotating point over time, we get pure sine and cosine waves. Their combined motion is simply circular motion. Frequency has a precise language. The time period t is the time for one rotation. Frequency f is how many cycles happen per second, and they are reciprocals. Angular speed omega is a direct representation of frequency f, where omega equals 2 pi f. The transform tests a signal by winding it around a circle. The Fourier transform essentially wraps the input signal around a rotating circle and sums up the position of the wound-up path over all time, finding its center of mass. When frequencies don't match, the path is balanced. As long as the test frequency does not equal the signal's frequency, the resulting wound-up path remains symmetric around the origin. The contributions cancel out, and the center of mass stays at the origin, making the integral result 0. When frequencies match, the symmetry breaks. When our test frequency finally matches the signal frequency, the contributions no longer cancel. They align and add up, pulling the path's center of mass away from the origin, which creates a peak in our frequency graph. The transform sweeps through all frequencies to find the hidden peaks. We test every possible frequency. A peak appears in the output graph only when our test frequency matches a frequency present in the original signal. The final plot reveals the signal's complete frequency recipe. The location of the peak tells us which frequencies are present. The height of the peak tells us the amplitude or strength of that frequency. From a chaotic wave to a clean spectrum, the Fourier transform allows us to see the hidden symphony within any complex signal. It provides a profound new perspective, turning a problem in the time domain into a simpler one in the frequency domain.